So this is the review from Chem 1 that I was talking about. Now, you may have learned that when you have a temperature change, when you have a phase change, like when a solid gets to its melting point and starts to melt, you have to continue to add heat, but the temperature during that phase change will not change. The temperature stays constant. And the same thing for boiling. You get water up to its boiling point and it starts to boil. You've got the water bubbling, but it stays constant at 100 degrees or whatever its boiling temperature is. And it just stays there. There's a graphic that I use all the time in Chem 1. You probably have seen this from your Chem 1 teacher too. It looks like this, where you have the solid phase. You know, this is temperature here, and this is heat added. So as we add heat, the solid raises in temperature until it gets to its melting point, and then it levels off, and we get that plateau where the phase is changing, but the temperature stays the same. And as soon as the phase change is done, when all the solid changes to a liquid, then the temperature starts going up again. And then we get to its boiling point, and then it stops raising in temperature and just flattens out like this. And then once it all has vaporized, then the gas can go up in temperature. Now I did this on purpose. I made this flat region bigger than that flat region because boiling a liquid always takes more energy than melting a solid. Because boiling, you have to get the particles completely broken away from each other, where solid, they just kind of relax their intermolecular attractions. You remember seeing that? Okay. So when you have a temperature change, in these regions where the graph is going up, as we add heat, the temperature is increasing. When you need to find the amount of heat, you use this formula, Q equals mc delta T. But when you get to the flat areas, you don't have a delta T. There's no change in the temperature. So we're stuck using these calculations of for how much energy is involved with melting a solid and boiling a liquid. I'll have the values of water to give to you too. Most of the time though, you'll expect to see the values for water right in the problem. It'll say the specific heat of water is whatever, or the specific heat of iron is. You'll get that. Yeah.
So the temperature doesn't change while it's melting or like while it's boiling, right? Right. But it can change after like it's
Yes.
Okay.
Yeah. So once you get water all boiled away, then steam can definitely keep raising up the temperature. Yeah. Just so you have them. Now you know that C for water is 4.18 joules per gram degree Celsius. The specific heat of ice is not 4.18, so don't mix those two up. Even though it's still water, as that different arrangement, it has a different specific heat. Ice is, I believe it's 2.1 joules per gram degree Celsius. And then when you have water vapor, C for steam is, I think it's 1.8. The book may have different values, but they're close to that. So all you have, the book gives you the C for steam, and it's not what I have here. Just use what the book uses. Lisa.
So like liquids always like the highest, or is it just the water? Is there like a relationship?
I don't know that one, because water is the only thing we use multiple phases for, really, when we're finding that. So I don't know if that's generally true. Because the density is different. Water as a liquid has a higher density than it's solid, so the solid floats. But that's rare. Most substances are more dense as solids than they are as liquids. So I don't know if we could translate that to specific heat too. I don't know that one. For water, the heat of fusion, how much energy does it take to melt 1 mole of ice? It's 6.01 kilojoules per mole. This is only for water. Other substances, other solids would have a different heat of fusion. But water is real common. You see water in all these problems. You'll need to know that. And also water for the heat of vaporization. It takes 40.7 kilojoules to boil a bowl of water. Yeah, Ethan? Yeah, yeah. Because all this is saying is that every bowl takes 40.7 kilojoules. So if you have 1.5 bowls or whatever, you just multiply by 1.5. All right.
I don't remember if we did this part or not, but for like freezing it, would you still do the same value as like melting but negative? Or?
Yes. Yeah, if you're going back the other way, you would use the same value. It takes the same amount of heat to melt a solid as it does to freeze that same liquid. It's just you put a negative sign in front of it if you're going the other direction. Everybody hear that? Just make it negative. Yep. So I have one problem to show you as an example of this one. It's terribly obnoxious. So I apologize for that ahead of time. It's probably going to take us 15 minutes to do this one problem. This is from the book, the good old Zoom dolls. You can depend on them to come up with an obnoxious problem. Number 99. I don't know if this one is assigned. I don't think it is assigned. Yeah, maybe I should go back and redo my homework assignment. Add this one in. How much energy is needed to, to raise 500 grams of ice from 20 degrees Celsius? This is ice we're starting with, but down below zero, all the way up to steam at 250 degrees. Yeah. So pretty much we have to cover that entire graph that I showed on the previous slide. If I were to do this, oh, that's kind of straight. We have solid, and then this is 0 degrees. Change to liquid with that melting region. And then as a liquid, it goes whoop up there to its boiling point. We'll call that 100 degrees. Then it boils with a lot more energy, and then it's going to raise in temperature once it becomes steam. So, I love this problem. So we have 5 different Q's that we're going to have to calculate. We can't combine all these Q's. All of them are going to involve temperature changes. This Q right here, we're going to use Q equals MC delta T because we have a temperature change. But then we get to this region where it's melting, and we got to use the Q equals heat of fusion times moles. I'll put M for moles. And then we get up to this part, and it's another temperature change. So we got to use Q equals MC delta T. Now, could we combine this Q with this Q? No. Different specific heats. This is not liquid water. That's not solid water. These are different, so they've got different specific heats. So you got to calculate this Q, calculate that Q for melting, calculate that Q for liquid water change in temperature. Then it's got to boil. So then we got to use Q equals the heat of vaporization times moles. And then once it's done here, that only gets to 100 degrees. Then it's got to go from 100 degrees all the way up to 250 degrees as steam. So that's going to be another temperature change, Q equals MC delta T.
Can you write
The Zoom dolls must have been laughing when they wrote this question. I bet they were.
Can you write the values for the going into like freezing and boiling?
What do you mean?
Like the going from ice to water. It's like the 6.1.
Yeah.
20, what's the gas?
Oh, yeah, you just did it again?
Yeah.
6.01 kilojoules per mole. Did you get the water too?
Yeah,
You get
I didn't
boiling?
get the bottom one.
Okay. Now, it's obnoxious, but now that we see it set up like that, it's not that bad, is it? I mean, yes, it's going to take us a while. We've got 5 Q's to find and then add together. A couple of things to be very careful about. 3 of our Q's the MC delta T for each of these three physical states. What unit do you get when you use MC delta T when you're solving for Q? Joules. What unit are you going to get when you use the heat of fusion or heat of vaporization times moles? It's kilojoules per mole. Yeah. The delta H is going to be kilojoules per mole, then you multiply the moles out. So be careful when you add these together not to mix the units. You've got to have them all converted to the same unit. Okay? Be careful with that. Ethan. Because it's water, we don't have to be told the boiling point. We know that it's 100. If it was any other substance, we'd have to either be given or look up the boiling point. Yep. So yeah, because we know the melting and boiling points of water, we know that that delta T here is 100 degrees. Otherwise, you'd be given those values. Did that just make noise?
No, it's
All right, you want to try that? Find all those 5 Qs, add them together, and see what you get. It's a pretty good amount of heat. I believe the answer is between 1,500 and 2,000 kilojoules. Yeah, you got that? Yeah. So yeah, if you got in that range, hopefully you got, I believe the answer was just from last hour, 1660 or so, 1,660. And I believe